Okay.
It's just the movie.
This one? So, and the mic. So YouTube officer, let me know as soon as the mic check is done. So it will take us some 20 to 30 seconds.
It's a bit quiet.
Bit quiet.
Well, no, it's okay.
So now it's okay.
Yeah.
So yeah, maybe because the mic was standing in that table. So
Yeah.
now the quality is all right.
Yeah.
Very good. You guys ready? Online participants, you ready? So let's go then. Simulation of a mechatronic machine, lecture number 9. Respect. Respect. Correct. Okay. Now what will happen today will be something that I'm sure you're looking forward to see today's lecture, because we're going to leave the multi-body system dynamics. We're going to move on to another discipline, and another discipline is a modeling of hydraulics. Modeling of hydraulics is conceptually very different than modeling of multi-body systems. The difference comes from many different ways. But first of all, mathematically, modeling of hydraulics is way more easier than modeling of multi-body system dynamics. So this is not involving some complex mathematical derivations or not complex equations at all. So this will be mathematically way more pleasant comparing the multi-body system dynamics. So that's a good news. The bad news is that it's also not as clear science or exact science as comparing the multi-body system dynamics. Because in multi-body system dynamics, everything is clear. So we know what are the parameters and what are the physical interpretation of different parameters. Now in hydraulics, I'm going to introduce a good number of parameters, and sometimes making a physical interpretation, how is the parameters and what they stand for, is less straightforward. And also it seems that we have to introduce some of the things that I'm just saying, okay, use this number because it's a rough estimation. And this is pretty much what is a hydraulic modeling. So it's not exact science, similar way than the modeling of multi-body system dynamics, because there, every single digit, we know how they're supposed to be and what they stand for. Anyways, I'm still thinking that this is something that it's quite enjoyable, and there's only a limited number of topics that we need to discover or discuss when we are looking at the modeling of hydraulics. And I'm thinking, this is my dream, that we can only use 2 weeks, and then we're done with the hydraulics. And then what follows is a little bit about gamification, and then the real-time simulation will be the full lecture about the gamification and the real-time simulation. And if we have any time left, then I can give you an overview about the flexible bodies. How is it you can describe deformable bodies in framework of multi-body system dynamics. But we'll see. My preference here, or what I would really like to do, is that I would like to spend a good time with the real-time simulation and gamification and game concepts. That's what's going to follow right after the hydraulics. So hold on. 2 weeks is a little bit painful, and then it's very, very enjoyable. But already when you're comparing today's lecture to, say, last week's lecture, you can see the big difference, major difference. And also, I'm still, thinking what happened last week, because the last week there were some outstanding comments and questions. Remember, I lost 2 lunches. I might mention to you, you're gonna get the 1 lunch, and a friend of you will get another one. Because of the comments, they were so good, and I promise that good comments is always worth of either a coffee or a lunch. So we'll see what's gonna happen today. But I'm kind of sensing, I'm not sure, but I'm sensing a little bit of love. We're getting to know each other. So we kind of start understanding each other. No? A little bit? A little bit, yes. Not love. Love may be too excessive, but a little bit understanding. So maybe we'll see how far this will go. Okay, so today's hydraulics. And this, again, is a picture that we follow when we are going through this course. So this tells how is it we are understanding a machine. And we are understanding the machine such that it consists of a number of different disciplines that are coupled together. Like they are coupled together in an assembled machine. So far we have discussed about modeling of mechanical components. But now, very, very important to understand that mechanical components that itself is not a machine. So we have to introduce an actuation. And the most common way to introduce the actuation, maybe I cannot say that what is the most common, but often used way to introduce the actuation is a hydraulics. But you know, what's very much in fashion at the moment is that there's a kind of the trend that people would like to replace the hydraulic actuators by electrical drives. And there are some benefits that are associated to electrical drives and some drawbacks as well. The major drawback associated to electrical drives is that the power density is not as high than in hydraulics. Power density means that the smaller size can produce a lot of forces. And that's where the hydraulics is very good. You know, if you think about the small hydraulic cylinder, you know, like diameter like this much, can produce enormous amount of forces. And this is very hard to do with any other means of actuators. So that's why the hydraulics is still needed, and it's particularly needed in the places where the mass versus power density is important. That's a mobile application. But problems associated to hydraulics is that you know, still the hydraulics is suffering quite a bit about energy efficiency. I mean, hydraulics as it is quite efficient when you look at like how is the efficiency of pump, how is the efficiency of hydraulic cylinder. All those are components where the energy efficiency is very high. But as a hydraulic system, as a simple entity, the energy efficiency may not be very high. And that's simply because of how is the design of the pump. Now, roughly speaking, the idea of the pump is to keep on producing energy to the system, and it will do that regardless if there's a need for energy or not. And this is something that I will introduce some latest concepts here that are like pump technology, you know, variable displacement pump, which is a little bit in that direction, and then load sensing pumps. Have you ever heard that before? No? Okay, what is that? That I will explain that to you as well. And then a little bit of something that is thought as a future of the hydraulics. And something that is considered as a future of the hydraulics is a digital hydraulics. So how is a digital hydraulics? That I will explain also in my lectures. But the big picture still is such that when you look at the actuators, most common or often used means of actuators is a hydraulics. But they could be electric drives. Pneumatics not so often when you think about the mechatronic machine. So mechatronic machine is something that there's typically feedback control of some kind. Pneumatics is often not used because pneumatics, which is air, is very flexible. And that flexibility introduces a complex when you wanted to use that in a feedback control applications. So that's why the pneumatics is not that often used. Then it's also possible to use water hydraulics, maybe some exotic like piezoelectronics, and those are also the means of actuators. The water hydraulics, by the way, that's quite interesting. The concept of water hydraulics is quite simple. So idea is to take the oil off from the hydraulics and replace that by the water. But that's nice because, typically the drawback associated to hydraulics is a leakage. There is some point of the life cycle of machine, there is typically a tendency of having leakage. A leakage is very nasty stuff because as soon as the oil comes out of the different components, they will make a big mess and everything look like a dirty and old. And now the idea, and also environmentally, if you think about the mobile machines, if you're leaking oil to nature, that's not good at all. Then you can maybe use a different type of the oils, to minimize the damage. Or then the wild idea is to use water. Water just to replace the oil. And this was something that was quite much in fashion, say 10 years back. Not so much anymore. But water hydraulics is one possibility. Water hydraulics typically is quite expensive when comparing to conventional hydraulics. And the expensive comes from the fact that the water as a lubricant is a lousy lubricant. And you have to use a quite expensive material in water hydraulics. So you typically need to use like ceramics or something else that is quite expensive. that's a little bit of problem in the water hydraulics. Another problem is that, if you leave water to a container, say that I leave water to this cap, and I leave it here to this cap for 2 months, and then I come back, and the water is no longer water, but is a cream liquid that grows monsters. There could be monster coming out from my cup, and this is, it's a big one. It can easily kill me, and that's simply because the water being in this container too long time. Okay, so what is it we can do with these monsters? Well, we can put a little bit of poison on this water, and that's the way to kill these monsters. But, remember this environmental aspect, and then this poisoning, they don't get along so well. So if you're using the water hydraulics, it would be a good idea to use just the pure water without the poison on it. But now that comes with the complications, because then everything is turned out to be green and sneaky and everything. So typically you need to use some ingredients that are not environmentally that healthy. But anyways, extremely long story, but let me get back to this hydraulics now. So let me stop here. By the way, your responsibility here is to raise your hand every now and then and say, Agi, speed up. We've been in this line already 20 minutes. We heard these stories about water hydraulics and so on. Keep on going. Can you do that for me? Can you do already this? Speed up. Okay, so let's see how is hydraulics. Well, here I have a few examples where the hydraulics is used. And I'm sure this is not coming as a surprise to you. So it's used often in different kind of cranes. Particularly it's used in the mobile applications and cranes that are used in mobile machines. And a good example is a harvester crane or harvester boom system that is shown in this picture. When you look at this picture, there is a hydraulic actuators here, another one here. There is a one here that is the one they produce a rotational motion. It's just a typical application of hydraulics. This is what you're going to do in your simulation assignment, similar to this. Now, regarding to your simulation assignment, I think that I need to change the color to make this more visible. So this one, and this one. Now, regarding to your simulation assignment, I don't know if you have already started this work, that assignment, but basically you have two possibilities to accomplish your simulation assignment. You can either use Atom software, and with help of these user routines that allows you to type in the equations, you can make a description of hydraulics. I think that many of you are using this option. So it's meaning that all the necessary equations that are needed in order to describe the hydraulics, you have to type them manually. And you know that this is a kind of not so pleasant work, because a minor mistake in your equation, when you do the typing, minor tuple in your system, and the system is not working at all. So it is nowhere near to work properly. And sometimes it really takes a while to find it out. There is a mistake. There's an alternative way to make your simulation assignment, and this alternative way will be based on Mecha software. Mecha software is a tailor-made for real-time simulation. So that's like a game engine, except that it's not a game engine. What it is not the game engine, because it's based on multi-body system dynamics, those very same equations that we are already familiar with. Now, there's kind of like the pitiful feature that comes along with that Mecha software is the fact that there's a graphical user interface to model the hydraulics. So it goes in such a way that once you have a mechanical structure ready, then you take an icon that is a representation of the hydraulic cylinder, you click it, and you say that the cylinder between these 2 points, and then you take another component that could be, say, direction valve. You say, here it comes. Hoses are connected here to here, and then you're just defining what is the diameter of the hoses. You're defining what kind of direction valve you're using, and what happens, background, is that the software creates the equations that describe the hydraulics automatically, and you don't need to type it anything. So that's another option. Now, how is that you can use this Mecha? This week tutorials, there is a another teaching assistant. So it's not going to be John, but it's going to be Manoncher. And the Manoncher is the one that is specialized in Mega software. So he will tell you how is it you can start the software, how is you can build the mechanical structure, how is you can build the hydraulics in that software. Now the beauty of the Mega is that you can also control the whole system by using the keyboard, the joystick, or whatever you want. So that's the beauty of, that's the advantage of real-time simulation. So either way, so you can use Adams or you can use a Mega however you want. Now, here's another example about hydraulic, something where the hydraulics is very important. So this is deflection compensated rolls that is used in a paper making process. You know, the paper making process is all about different kind of rolls and the paper machines that are very masculine. I hope you've seen those machines. There's one in this city, a little off of the city center, and it's making a big noise, and it's a monster machine. You know, if you think about like a tractor is a monster, it's not. Paper making machine, that's the true monster. You know, it's like, I don't know, 200 meters, you know, long, and maybe 10 meters wide, and make a lot of noise. More noise, the better it is, I guess. Well, I don't know. Anyway, so the machine is full of different kind of rolls, and the rolls are pressed together. And now, when you look at the machine in this this longitudinal direction, you know, when you have a roll like this, it's clear that because of the gravity, the rolls will be deformed. They will be deflected. And they will be deflected in a certain way, like a little bit like this. And this is a special roll that is made in order to compensate the deformation due to the gravity. How it happens? It happens in such the way that, you know, there's a shaft, this one here that is standing still, so it's not rotating. Then there's a cell, and the cell is the one that is rotating, and that is the one that is pressed against another roll. What is between these two components is a hydraulic loading shoes that are acting like a zonal bearings, but special kind of zonal bearings. Kind of the zonal bearings that can introduce the forces in order to, you know, to compensate the deflection. They can either also introduce a different kind of profiling, not just to compensate the deflection. And this is what is used in a paper making machine. Now, why is that I'm telling you this application? I'm telling that because, you know, I haven't mentioned much about my background, but I have a like dark background in sense of, you know, university life. And if you want to stay in university, you better stay in university, not to leave from university. But when I got my doctorate degree, that was a couple of years back, not so many years, 21 years ago. Well, as soon as I got my doctorate degree, I went to industry, and I was involved to a company that was making these paper machines, paper making, you know, paper machines. And my specialty at that time was related to this particular type of roll. So I was a specialist of this particular roll. So that's a little bit about my history. Okay, then I want to show you some animations. Okay. I think it is loading something. I thought that I loaded already before the lecture, but I want to show a few animations, like how is this different components, or how is this harvesting crane, how that is operating when the hydraulics is modeled. And particularly I wanted to introduce how is MEVA software, and how is that you can actually model the hydraulics in MEVA software, because that is something that is quite beneficial. Just when this is downloading the file, there was a feature in Adams a while ago available that allows you to model the hydraulics by using just the icons. Because of course, in practical work, when you work in industry, you don't have that much time that you can type all the equations that are needed in order to describe the hydraulics. Because the real hydraulic circuits, they consist of quite a large number of different components. And now to make a model like that describe everything in details, that needs a serious typing work. And now this typing is very prone for any kind of errors. Now if there is even a minor error, the system will not work. And sometimes debugging can take too much time to find it out. So that's why these kind of graphical user interfaces are needed. And how they look like, that I would like to show you by demonstrating that Mevia thing. But still loading it. Should we leave this for after break? Now, just when I'm gonna press it, okay, forget it then I'm sure it's coming. Let's forget it. Now we'll solve this right after the break. And let's look at what we can do with the hydraulics. So this is a movie about the Mevia and how the Mevia modeler is operating. And it's beautiful. And it allows you to create very complex hydraulic circuit within a reasonable time range. Okay, so the first topic. Let's get started from the properties of fluids. That's the first item that I would like to explain. And what I'm going to do is that I'm going to first explain you the bulk modulus, and then I'm going to explain you viscosity. My first in-class quiz will be related to bulk modulus. And I'm asking, listen to me, I'm asking what is the physical interpretation of bulk modulus? That's what I'm going to ask, seriously. Now listen to me, and you will find it out. What is the physical interpretation of bulk modulus? Do you already know what that is? You do. You don't. You're going to find it out soon. So let's take a look at the bulk modulus. So two items that I'm going to explain are the viscosity and the bulk modulus. Another one is not so important for us. The one that is not very important for us is the viscosity. And why it is not very important for us? That's simply because the viscosity comes into play when the flow type is a laminar flow. And typically the laminar flow, you don't know what are the flow types yet, but roughly there are two flow types. There are turbulent flow and the laminar flow. And the laminar flow is something that takes place when the pressure difference between the two different volumes where the flow is actually connecting is low. The pressure difference is low, say roughly speaking less than 5 bars. Now, in mobile applications and most of the industrial applications, the pressure differences are large. So we speaking about 50 bars, 100 bars, even more the pressure difference. And in that case, the flow is not the turbulent, is not the laminar flow, but it's a turbulent flow. In a turbulent flow, theoretically, the viscosity is irrelevant. So that's why the viscosity is something that is good for you to know, but we are not going to use it extensively in our simulation. But another feature is extremely important, and that's the bulk modulus. The bulk modulus affects the stiffness. So the physical interpretation of bulk modulus is that it is representing the flexibility of fluid. And this is extremely important. So yeah, look at the in-class quizzes, and it's already on. So you can log into system, and the first question is available. Can you see it? You know what my dream is. In addition to get the new computer, but there is another dream in my mind. You know what that is? Is 100%. So we'll see how it's 100% today. But the bulk modulus is something that accounts the flexibility of the fluid. Now every now and then you hear that, okay, now the flexibility of fluid is something that is non-existing, so it's rigid. Well, sometimes computationally it may be considered as a rigid, but of course it is flexible. Of course it is flexible. And just to give you an idea what it is flexible is that, what happened in this lecture here, I'm talking here, and when I'm talking there's a vibration that leaves from my mouth, comes to your ear. In some cases, it goes inside of your brain and your understanding. But at least what happens is that the voice comes here and it ends to your hearing. Correct. How is that possible? That's simply because the waves traveling back and forth in this space. Now, what would happen if we would fill this place with the water? We don't necessarily need to do oil, but just the water. You go under the pool when you're swimming. When you're yelling to your friend under the pool, you can hear it. Maybe you can hear it like like this way. But you don't necessarily understand that. And what's happening there? It happens such that the waves are traveling back and forth in water. And that simply tells that in order to travel back and forth, it must be flexible. Otherwise, it's not possible to hear what someone is saying under the water. So that's just a simple proof that the fluid is flexible. And often in practical applications, when you look at the source of the flexibility, it may be because of the mechanical components, but very often the flexibility is due to the hydraulics. The hydraulics is quite flexible, and often because of the compressibility of actuators, it can introduce significant deformation to the system. Okay, and that all we can account by using bulk models. So this one here. Now, let's move on. How is it we can define the bulk models then? Now, in order to define the bulk models, we need to set up the experiment here. And the experiment is such that I have the container, the green in color. So this one here is a container, and I'm assuming this container to be something that is mechanically rigid. So it's unable to deform no matter what. And then I have here a lid in this container, and the lid too is rigid. So there is no deformation whatsoever. And inside of this container, there's a liquid. There's a fluid here. What I'm going to do then is I'm going to take a force. You need sometimes maybe you use quite a hard, large force. Force here, and you press the lid. Now, what will happen then? The lid will compress a little bit. It may be go a little bit inside of the container, but what will happen for sure is that the pressure inside of the fluid will actually increase. Correct. So the lid will go down a little bit, and the pressure will increase. All right? That's what's going to happen as a consequence of this force here. Now, the bulk modulus is all about the relation between the pressure change and the volume change. By the definition, that's what the bulk modulus is about. So how much the pressure within this container is increases versus how much the lid is getting down, that's equal to how much the volume is decreasing. That's the definition of bulk modulus. Now, okay, if that's the definition of bulk modulus, it's clear that numerically the fluids, the bulk modulus of fluids are very high, particularly when comparing the air. Air, you take like pump, you use it in order to inflate your tires in your bicycle. You can easily close the one end of the pump, and you still can move the piston back and forth. That's, what will happen inside of the pump is that the pressure will increase, but not so much, but the piston will move quite significantly. That already tells us how much more flexible is our air comparing the fluid. All right, and the difference is typically like 1,000, 1,500, could be even more than that. So that's the definition of bulk modulus. Now, what I did not mention here is that the container is assumed to be unit in a size. And I want to generalize this concept, so I don't want to always discuss about unit size containers, but all size of containers. So how is that I can generalize the concept? I can simply generalize the concept by dividing this definition by the volume size. That's it. Now, my bulk modulus as a definition is minus volume size multiplied by pressure change divided by volume change. That's what it is. Now, the bulk modulus in reality is a function of number of different things. It is a function of the pressure that affects the fluid. It is also a function of temperature. And here is a unclear picture, but just to show you an idea, I have here different curves. This is a bulk modulus. Let me explain to you here first. So what I have here in this y-axis is a bulk modulus. And the numerical values, what I have here is this is a 1,500 megapascal. This is 2,000. This is 3,000, and so on and so on. And then what I have here is a temperature. This is 10 degrees. This is 100 degrees. So here's 100 degrees, and this is 10 degrees. And then I have different curves that representing different pressures inside of the fluid. Now, the two curves that are important for us is the zero pressure curve and then the 250 bars curve. Typically, this is a kind of the limit what we're using in hydraulics, not the pressures higher than that. And now you can see that, yes, clearly, the bulk modulus is a function of temperature, and it is also a function of pressure. Here's the first very important assumption we can introduce in hydraulics. And by the way, this is pretty much what the hydraulic modulus is about. Modeling is about. So I'm introducing something and then I'm saying, okay, let's make an assumption. So the first assumption that I'm introducing here is that I'm simply saying, okay, the bulk modulus will have a constant value. Bulk modulus of the oil will have a constant value. The value that I recommend you to use is a 1,500 megapascal. Clearly, you can see from this picture that this is the value that I'm introducing here is not exactly true because it's a function of temperature, function of the pressure. But it's all right assumption. So that's it. Okay, so that's bulk modulus. Now, often, well, practice always, there is no such thing like rigid container. You know, there's always a container flexibility that may affect a little bit about the flexibility of the fluid. Typically not so much if we're speaking about, you know, hydraulic cylinders that are made out of the steel material, but often there's hoses that are used to connect the direction valves and hydraulic cylinders. And those hoses are made out of the rubber material, and rubber is quite flexible. And even though that there is always a steel net around the hoses, still the flexibility of the hoses can be very significant. And then another factor that often is important is the amount of dissolved air, because no matter how carefully you do the assembly work of the hydraulic circuit, there's always a little bit of dissolved air in your system. Air, as I mentioned, is up to 1,000 times more flexible than the fluid. Now, even a tiny amount of air will introduce a significant difference in the flexibility. So that's why those typically need to be accounted. Now, how we can account these different factors? We can account them by using something called effective bulk modulus. So in the previous slide, there was a definition of bulk modulus. Now, the effective bulk modulus is something that all these factors, flexibility of container, flexibility of dissolved air, all those will be accounted. And that's what we're going to take a look at next. Now, in order to calculate the bulk modulus, this, by the way, is a little bit related to where we define the pressures in the hydraulic circuit, or how we're using the concept called wound fluid theory. We have to account the flexibility in all the containers that are connected together without the pressure losses. So that's exactly what we're going to do next. Prior to that, so you're pretty quiet today. That's because of trip to Russia that took all your energy, or something else? Any comments or questions so far? So you went all over the different places in Russia, or just St. Petersburg?
Just
St. Peter.
Okay. So how was the Russian vodka? No experience? You don't know? Okay. So no comments or no questions this time? Clear? All clear. Okay, so let's go on. Okay, so always we can take a look at the effective bulk models. Now what I'm going to do then is that I will modify the experiment in such the way that I'm going to actually use a system that consists of two containers that are connected together such that there is no pressure losses. So what that means? It means that if I look at how is the pressure within this container, the pressure that is a right corner, you know, this particular location of the first container, the pressure will be here, will be same than lower right corner of the another container. So So the meaning that there is no pressure losses when you look at the particles or when you look at the fluid within these two containers. And now what I'm going to do then is that I'm going to calculate the part modulus, effective part modulus, which is a description of flexibility for this system that consists of two containers. Okay, so I have here amount of fluid that is in the first container. So this is amount of fluid that is the first container. Then I have amount of fluid that is in the second container. Those are the locations where they are. Now, amount of fluid and the size of the container, they're actually very same in this initial configuration. So the VC1, VC2 is a container size. So initially there is all the same. Now what I'm going to do then is that I'm going to introduce the change in the volume. How can I do that? I'm cannot tell you that, but I'm going to simply kind of like pressing that by using a lid that there's a lid and I'm pressing to this direction to this system. What will happen is that the fluid will compress. They will go to smaller volumes, whereas the volumes, these containers, they will get bigger because of the mechanical deformation. So this is how it looked. So if I introduce the volume change, the oil will become smaller, containers become larger. Correct. You're with me? Because that's exactly what's going to happen. So let me solve this slide here. So if I will compress this, hold on this lid downwards, the fluid will compress and it will go down here, but the container will get bigger and it will go all the way here. Extreme picture, but still, get the idea. The one gets smaller, another one gets larger. Correct. All right. So that's what happened in this experiment. Okay. So then what I'm going to do then is that I'm going to use the definition of bulk modulus that was introduced in the previous slide, and the definition of bulk modulus was simply volume size divided by pressure difference, multiplied by pressure difference divided by change of the volume. Okay? So now I'm going to introduce this concept, the total volume, the fluid in a container 1, fluid in a container 2, container 1, and container 2. When I'm going to substitute this information to my previous equation that was shown in the previous slide, I will get the equation as it is written here. So now what I'm going to do then is that I finally will divide all this by volume size, the total volume size, and I will get the equation as it is shown here. This equation is the effective bulk modulus and is accounting the flexibility of the container and the flexibility of two fluids. And I can even introduce a little bit of simplification here. So with assumption that the total volume, hold on, here, total volume is the fluid number 1 plus fluid number 2, and the fluid almost same. I mean, the total size almost same to the container size. In both cases, I can write my effective bulk modulus as is shown here. Now, what comes next is a little bit out of the blue sky. I'm saying with a similar way, I can account the amount of dissolved air. So I'm going to simply add in one more component to this equation, and the one more component that I'm adding is the same principle, but except this time I'm accounting the dissolved air. How is that? So I have here, what is the volume of the air? Then this is a total volume of the system, and this is a flexibility of the air. Once I have that, that's the equation of my effective bulk modulus. Look what I have here. This is the effect of flexibility of fluid. This is the effect of deformation of container number 1. This is the effect of deformation of container number 2. And this is the effect of dissolved air. That's what it is. Now, how is this air, how that is introducing the effect to effective bulk modulus? Here is an experiment that shows how is effective bulk modulus in case of 0% of dissolved air, which is a curve shown here. So curve number 5. I need to change the colors of this curve here. Then there is 2% of dissolved air, which is this one here. You can see that it's affecting all the way to when the pressure is say 160 bar. So it's most often it is make a little bit of contribution. And then this is 5%, this is 10%, this is 15%. Is it? No, I think I explained this in the wrong order. Hold on. No, this one. So it goes all the way around. So 5, this one here is a 0%, is this curve here. 4 is a 2%, and this curve here. So it only affects when the pressure is say 100 bars and less. So when there's more dissolved air, like extreme cases, 15%, then it's affect all the way when the pressure is 160 bar. Okay, this is a simple equation that is coming from the strength of materials, and you can use that in order to evaluate the flexibility of the containers. This is an experiment that is coming from the case where people are measuring how much hoses are introduced into flexibility. And this is how it affects the effective bath models. Now look at the numbers what I have here. You know, the flexibility of the oil was 1,500 megapascal. And now when you have hoses in your system, it goes really quite much down. You know, here the number is 320 megapascal. So that's the kind of the scale, how much more flexibility is introduced because of the hoses. So hoses are quite important source of flexibility. Okay, then there is something that you need in order to answer this week in class quiz, but I can see that it's almost time for a break. So before the break, let me ask you this. The bulk modulus in hydraulics describes force produced by a cylinder. First option, flexibility, compressibility of hydraulics, oil amount in the circuit, number of components in hydraulic circuit. Okay, so let me see. Okay guys, please log into system. What you will see very soon is a happy face. You know why the happy face? Because of the 100% success rate. Today is the day. Today is the day. It is. It is. Believe me, it is. Okay. Let me go over these options again. Force produced by a cylinder, that's one option. Flexibility, compressibility of hydraulics, oil amount in the circuit, number of components in hydraulic circuit. Only one is correct, but which one? This is quite easy, I would say so. It is extremely easy, is it not? Quite easy. Okay, so then once you're done with this, by the way, how come we only have 22 students? Do we have a problem in the stream?
No.
How many people are following the stream?
33.
How many?
33.
How come? Okay, so why is the people are not, is it the me that is, this is not updated, or what's wrong?
Maybe they have chosen the answer before you put it in the screen, so that's why it's not counting now.
It should be.
Maybe they need to answer it again.
Hold on, so let me see. Oh, no, there's more people coming. Is it? No. Okay, so all my participants, please log into Socrative and please select the room LUT. And select the one that is correct, and these are the 4 choices. Okay, now that, no, okay, it was just one more student. Should I just close it? Oh, no, there's, no, now more is coming, okay. Maybe the delay is not just the 20 seconds, but, I don't know, 10 minutes. Get me that. Because this system for sure is a real-time system. Streaming kind of real-time, except that because of the delay, is not exactly real-time. Still, only 28 students. Anyways, kind of slowly coming more. Okay, you guys have a break, so let's have a break of what I said, 10 minutes. 10 minutes. And then we're gonna shortly discuss about the viscosity. We're gonna look this movie about the Mever, and then we're gonna discuss about lump fluid theory. Before you guys leaving, lump fluid theory is extremely important in this course. It is, you know, if you think about like what are the important concepts, it's maybe the most important concept. So make sure you're coming back and make sure you pay attention. So go and get some coffee, make sure that you have full energy, stretch yourself a little bit, and then get ready. Okay, 32 students. So what if I just close it? Is it gonna be 100%?
No.
Yes.
Try.
Yes.
Try.
Okay.
Let's go.
Okay. Ready?
You have to give us a coffee for everyone.
I will. If it is 100%, I will. You know, getting coffee for you guys was this close.
We can get you up.
I think there's just one person who answers.
My friend told me that his dog answered the question. That's the screen with his paw.
Really?
Yeah, the dog answered. So it wouldn't count.
Yeah,
Okay.
and I think this is just one person for 3% because there are 32 of us.
It is, but it could be you that answered correctly. So you never know.
Maybe the dog answered right.
The only person that knows this is me. That I don't release that information.
So no free coffee today.
No free coffee.
Oh.